Today we're going to start lecture 3, Capacity Planning and Engineering Economics. So the outline for today is it includes both parts, capacity planning and engineering economics. So capacity planning mainly deals with how do you plan out the capacity or the best service level of a manufacturing system, while engineering economics are mainly dealing with cash flows and how to calculate the economics related to projects and on equipment or the major projects or interest rate. All right, so there are going to be a lot of calculations in this lecture. This is probably the most calculations in this whole course. So pay attention to the lecture slides and also the video, and then hopefully you can get what are the ideas behind the engineering economics and capacity planning. All right, first, capacity. Now we need to understand what is capacity. Capacity is the amount of resource inputs available relative to output resources or requirements over a particular period of time. So it includes both parts in the inputs and outputs. And strategic capacity planning basically is to provide an approach to determining the overall capacity level of capital-intensive resources, facilities, equipment, or labor for size that best supports the company's long-term competitive strategy. So this is strategic capacity planning. Two concepts here. One is the best service level or best operation level. So best operation level means the maximum capacity you can reach of your whole production system. While the capacity utilization rate means what is the rate that your capacity actually used compared to the best operation level. So it's a rate. All right, now let's look at let's use one example to demonstrate how it works with those kind of concepts. So suppose we have a factory that is producing phones, right? And our factory has 5 lines, and each line there are 20 workers. And for each line each day, we can produce 2,000 units, right? So actually, from the calculation, we can tell that the actual production for each line will be 1,500 units. And so from this, we can tell that now it's asking what is capacity, what is the best operation level, or what's its capacity used and the utilization, right? We know the actual production volume or actual production operation is 1,500 units, while the daily units, the maximum capacity can reach is 2,000, right? So from here, we can tell that we can calculate what is the best operation level, right? So the best operation level will be using 1,500 to divide it by 2,000. Now you can get, so this should be 75% of the best operation level. Right? Well, what is the capacity? Now you can know that with 5 lines and 20 workers for each line, the capacity is 2,000 units per line per day, right? And then what is utilization? Utilization basically is only 1,500 units per line. All right, so next let's look at the different ranges of capacity planning. So the capacity planning, it really depends on the time horizon you're looking at. Some of the decision has to be made in a really short time. For example, it's less than a day or less than a month. While some of the decisions will have to be made probably several months or quarterly. Well, in this case, they are called intermediate range. So usually that's about months or quarterly plans. And there are also longer plans that is over 1 year or even multiple years. So that is called long range. and those projects can probably be related to facility building development, or some other plans related to maybe new product development or something. Well, short-term range plans probably related to some supply chain decisions, getting the materials, scheduling, all these kind of decisions. While intermediate range of the plans probably related to how do you make the forecast for the next month, or some of the schedules related to material storage, or resources planning, right? All right, now suppose that we are developing a phone, and we have a factory of making this kind of phone. The demand increased, right? So originally we have like 2,000 units per day. Now the demand actually increased. It is asking for 15,000 units per day. I think originally we have 10,000 per day because we have 5 lines. Each line is 2,000, so that's 10,000 units per day. Now it is increased by half, so the demand increased by half. Now the question is, what should we do, or what should you do as a CEO or manager of this company, right? Because we have a large demand increase, and there are a lot of orders. But our current capacity cannot meet them, the customer demand. So what should we do in order to earn this money? Because these are potential benefits if we make them. All right, so there are really several different ways we can look at to increase the capacity for our production. So one is we are looking at it more internally. So internally, we're not thinking about how can we increase the efficiency of our production systems. For example, we probably can extend more hours. Instead of one shift, we can probably work on 2 or even 3 shifts per day. This is one solution. Or another solution is probably going to evaluate what is efficiency of our existing system during one shift. For example, there are too long of the lunchtime, or maybe there are too long of the breakdowns of the machines. Then we will probably need to find a way to address those kind of issues. Well, another thing is we can look at the balance of the processes and find out what are the bottleneck stages, right, or the bottleneck process. Then maybe you can, by splitting some of the processes, to reduce the cycle time, so we can get more efficient in production. Another one is to build in some buffer inventories. So buffer inventories means there are some kind of bottleneck stages, and sometimes the materials probably cannot get into a process. For example, we have process 1, process 2, process 3, and when there is a lot of raw material parts accumulated at process 2, because process 2 has longer processing time, then 3 will have to be idle, right? Because this 2 is taking too long. So 3 will be idle a lot of time, and I cannot make anything. Well, so one way is we can probably make some existing or pre-made parts during some extra hours, or some other time, in order for 3 to be processing that process, normally. In this case, the rest of the process at 4 or 5 can just, keep moving smoothly, instead of, waiting a long time at 3, right? So this is the one way that you can build in some buffer inventories in order to make your production line move smoothly. And there's the one term in lean production is called Kanban system. So the Kanban system is to build at each of the process to build a certain small inventory. Remember this word, small inventory, right? You don't want to accumulate a lot of parts for storing and increase the storage cost. It's a small inventory that you can always keep the parts moving on the floor, because if the parts are not moving on the floor, means you are spending more money or wasting the opportunities of making more money. So this is how you can balance and keep your parts moving on the shop floor. Another one is duplicating or increasing the facilities of one department on which. So this means that if it is two for this process, 1, 2, 3, 4. Well, if two, for example, it need 8 minutes, well, one only need 4 minutes, and 3 maybe 4 minutes, and 4 maybe only need 3 minutes. Well, because process 2 has a really long processing time, then what we can do is we can split 2 into maybe 2, 1 and 2, 2. And each of the operation will only need 4 minutes. Well, in this case, you are actually looking at the process what? 1 to 1, these processes. So this is our new process. And originally, our cycle time is 8, right? Remember, the cycle time of the whole production system is actually based on the longest service time of each of the operation, right? So in the first scenario, it's 8 minutes. While in the second scenario, after we make this change by splitting 2, we actually have 4 minutes of cycle time. So this is the one way that we can achieve a reduced cycle time by duplicating or splitting a long processing time process. Well, another way to increase our capacity is to look at some external sources or resources. Maybe we can work with another company or outsource the operations to another factory to make the parts for us, right? So that's another way we can achieve this. And next, let's look at another two concepts. One is economies of scale. Economy of scale means when the plant is getting larger and larger and the volume increases, the average cost per unit of output actually drops. So the reason for this kind of drop is because when there is an increase of demand, usually the company tends to invest more money into production. Even though that the demand keeps a really high demand, still the cost of it will increase because those kind of facilities investment won't be able to generate much of the profit. Let's look at one equation so we can demonstrate it better. For example, now let's look at the cost per unit. So cost per unit probably equals to what? There's two different kind of a cost. One is the fixed cost, the other way is the variable cost. So the fixed cost means when we produce the product or when we are making some of the products, we have to invest in certain facilities, right? Those kind of fixed facilities. For example, the building, right? The cost of building. And let's call it some other facilities or equipment. Facilities and equipment. For these kind of the costs, there can be more like this, kind of fixed costs. And for this kind of cost, what happens is that regardless that you produce parts or products or not, they are always there. Right? They are always there. It does not depend on how many parts you are making, right? So it's always there. And there's another type of cost, which means that what? Means with a higher volume of production, of the products, actually the cost will increase, because the more you make, actually the more material you will need, and material cost is a very typical part. For example, material cost will equals to what? Equals to cost of materials, right? The single materials times what? Times the demand, right? Times demand, or the output, how many you make. While the cost per unit will be using the upper part divided by demand, right? So from this equation, we can tell actually the cost of the units is really an equation of C building plus C cost of facilities and equipment divided by D plus what? Plus C materials. C materials. Now let's look at it. If we get a lot of increase of this, right? If we get a lot of increase of the investment into building and facilities to increase our capacity of production, actually the cost of units will go up, right? When this is go up, cost of units go up. Well, when we increase the materials, so if we increase the demand of materials, this does not change, right? This does not change. But when we invest in more capacities or infrastructure improvement, then the cost of units will actually increase, and we will make it a lot harder to probably we'll get our benefit lower. So this is why they call it the economies of scale. And diseconomies. So this is what it means. You can tell from this equation. All right, next, focused factory means when you have the factory, in order for you to keep your competitiveness, it's better that you focus on a certain series of objectives, which is have the key competitiveness. Because if you keep expanding or focusing on a lot of other different aspects, sometimes you lose your focus and lose your core competition. So this is why a lot of factories actually fail eventually by always shifting objectives, shifting goals, by producing this and that, all different things. But they gradually are losing their core competition. And also, when you have a factory, you probably also want to make your capacity more flexible. Flexible means you can make more products if the demand increases, because there are certain flexibility embedded in the efficiency, or embedded in cycle time allowance. Those kind of things you can work on. Well, another thing is by flexibility, it also means you can produce more models, right? For example, well, if currently we are producing one kind of a phone, and when there's another phone order came but from another different model, then our factory actually is able to make, just by making certain justification or modification, we can actually start to make another model. So this is also the capacity flexibility you want to build in when you are designing or improving a manufacturing system. Not only this, but also the workers. So when when you have a bunch of the workers on the shop floor, you probably want to keep your workers not only just can operate one single process of machine. Instead, you might want to always keep them shift into different processes so they can be more flexible in operating different machines or different processes. And this is how you can keep those workers more competitive and also develop their own abilities in adapting into different environments in production. All right, now let's look at another scenario that if the demand decreased, what should we do with our capacity, right? Just now the scenario was demand increase. We listed several different ways we can increase our capacity. Now the demand decrease, should we do? Now the company is actually asking for 5,000 units per day instead of 10,000 units per day. All right, so for decreasing capacity, there are really several ways. Really, it depends on is it a short-term or temporary decreasing, or is it permanent decreasing. So if it is a temporary decreasing, then we probably want to schedule less hours, or reduce our capacity a little bit during the day, by make our cycle time maybe a little bit longer. But still, there are a lot of work to do. Or we can schedule the workers to work on some other buffer inventories in case that the demand will increase later. Okay, so these are the temporary strategies. Well, if there are really permanent strategies, then we really have to sell our equipment. Right? Or we can find some other market opportunity. For example, making our resources available to make some other models. Now we can back to the flexibility concept, right? Make our production line more flexible, so we can make different models or different kind of products. Another way is we can also outsource or lend our equipment or our space to some other factories or some other companies. Right? So these are different ways we can work on if we experience a decreasing of capacity. All right, now let's look at one example to find out how do we calculate person utilization, machine required, or labor required if we have different demands. So this is one example that says our factories we have 10,000 units per day, and we can produce 10,000 units per day and 2,000 units per machine, and 20 operators per machine. So we have 5 machines. This is our condition of the factory. Now, in this table, we listed that monthly requirements or monthly demand from the customers. In the first month, we need 250,000. In the second month, 200,000. Third month, 150,000, and month 4 is 125,000. All right. So now, in order for us to calculate or plan out our labor, our machines, first we want to find out is what is the percentage utilization rate of our capacity, right? Now we need to calculate what is our full capacity that we can make. Right, the full capacity our can make is 10,000 units per day. Well, if it is going to make 10,000 units per day, how many? It is monthly. So for a month, we can actually make 300,000 per day, assuming that all the 30 days are actually working days. Okay. So now we can use 250,000 divided by 300,000. Now we get a percentage, which is 83.6%. 83.6%. Similarly, we can calculate the rest of the utilization rates, right? So the second one should be 67.7%, and month 3 is 50%, and month 4 is 41.7%. Okay. And the number of machines required. So because we already have this percentage utilization, then we can actually use the percentage utilization times the how many machines we have, right? So simply use how many machines we have? We have 5 machines. So 5 machines times 83.6, right? And this will be 5 machines times 67.7%, and this will be 5 times 50%, and month 4 will be 5 times 41.7%. Okay. Then you can calculate how many lines they actually require. Then you probably want to run it up to a integer in order to be a full line. Same with labor. So the total number of labor we have is 20 operators per machine, and 5 machines we have 100, right, operators. So 100 times utilization rate, 83.6, right? So it'll be 83.6, run it up to 84. And month 2 will be 67.7, run it up to 68. This will be 50. It will be 41 times 7.7, round it up to 42. So this is how we calculate the capacity or the resources that needed in order to, if we know that what is the percentage utilization and also demand. All right, so this is one example. Now let's look at another example of evaluating different capacity alternatives. For example, so assume that labor cost in our city is increasing. We are investigating 3 different alternatives. So one alternative is we want to move to a new location because in our local place the labor cost is really high, and maybe we are not generating a lot of profit right now. But there are some options that we can potentially reduce the labor cost or to generate more profit. Now we're evaluating different options. So the first option is move to a new location, and the second option is expand our existing capacity. Third option is do nothing. We still keep the doing what we are doing right now and see how it goes. All right, so on this condition, regardless of which alternative we choose, there is a market that probability. So the market probability is 55% of the chance that we have a strong growth, and 45% of the chance we have a weak growth, right? Because right now we do not know it is strong or not, right? This is only one prediction or a guess or estimation. All right, so and it's based on the probability. Now the conditions are, so if we move to a new location and if we increase the strong growth, what happens is our annual revenue will be 195,000, right? But if we move to a new location and if we experience a weak growth, then the annual revenue will be 115,000, right? Similarly, we have some other numbers related to if we expand to existing capacity. What is the annual revenue with strong growth? And what is the annual revenue with a weak growth? Same with do nothing, right? All right. Another condition we know is that if you want to move to a new place, there's also a cost. Moving cost, right? Is also a bunch of money. So moving cost to a new location is 210,000. And if we expand our existing capacity, is 87,000 money we need to invest, right? So given this condition, now the question is, what should we do, right? What should we do? What's the best alternative comparing of the three alternatives? All right, so Someone may ask, because we do not know what's going to happen, so how do we calculate, how do we evaluate those kind of three options? Well, because it's the future and there's some uncertainty, so all we need to do is we use probability to calculate, right? To calculate the future, right? To give estimation of the future. So it's like, for example, I like to use this example to demonstrate using probability and means. All right. So suppose you are going into a very fancy restaurant in New York, right? Downtown New York. And a really fancy restaurant, and you look at all the menus, right? You look at all the menus. So among all the 100 dishes, right? 95 dishes are above $100, right? Each dish is above $100. There are only 5 dishes, right? Only 5 dishes that is what? That is less than $10. Only 5 dishes are less than $10, but 95 are above $100. Okay. Now the chance is, okay, what you're gonna do is you're gonna close your eyes, and randomly point to a dish, and you're gonna order. Right? Randomly point to a dish, you're gonna order on that menu, and you will order that. So now the question is, give you the estimation. How do you gonna estimate how much money you're gonna spend in this restaurant? You probably say, oh, there's really high chance you're gonna spend over $100, right? So this is how you use probability to actually estimate how much money you're gonna spend. Well, compared to the downtown New York restaurant, now think about if you go to McDonald's, right? Same thing. You randomly point to the menu and then select the dish you want to order. It's likely you won't spend more than $10 or $20, right? So this is the chance that how do you use probability to find an estimation. All right, same with this. We have the probability of strong growth and weak growth. Now we need to find out how much revenue is actually generated based on the strong growth probability with strong growth revenue, and based on the weak growth probability with weak growth revenue. Then we come up with this table. So this table simply describes for each of the scenario what's going to happen, right? For example, if we move to a new site with a strong growth, and the probability is 0.55 and the revenue is 195,000, but also there's a cost $210,000, and we use the revenue times the 0.55 and do what? So use this revenue, and also we have the cost. So suppose we are doing the 5 years planning. Right? So we are using the 5 years planning. We use 5 years times this revenue minus, right? 5 years times this minus 210,000. Then we get this number. Yeah, get this number. And same here, we use 5 years times this and minus the moving cost, get this number. But this 765,000 is based on the condition that it's for sure. It's for sure that it's moving in strong growth, right? And 365,000 revenue is based on the chance that it's for sure it is a weak growth. So now we need to calculate what is predicted benefit. Then we use what? We use probability, right? Or we use the mean. So use this value times the probability, and this times the probability. Then those added up together is the whole chance, right? 100% of the probability. And then we can calculate 585,000. So 765,000 times 0.55 plus 365,000 times 0.45. Then we can get this 585,000. Similarly, we can calculate if we expand our factory, how much, what is predicted benefit. If we do nothing, what is predicted benefit. So from the calculation, we can tell that actually do nothing yields the more benefit from this. Well, an interesting question is, this calculation is totally based on a 5 years benefit, right? 5 years benefit. Maybe do nothing is the best option. But what about 10 years? What about 15 years, 20 years, or even 50 years? What's going to happen? So maybe that's an interesting topic that you can do the calculation by yourself later, okay? All right, then next, I want to come to the engineering economies. So engineering economies mainly are dealing with how to calculate the money, right? So then everything is talking about money. And from our prior example, you can see the 5 years benefit is actually based on the condition or based on the assumption that there's no inflation, right? So no inflation at all, and every year the money is the same. But as we know that it's not the same, right? There's a time value of the money. And that's why engineering economy is going to come into play in long-term plannings, especially related to equipment, project, or strategies. And all right, so first, two concepts related to this is a simple interest versus compound interest. So simple interest means interest is only computed only on the original sum and not on accumulated interest, right? For example, right, we have an initial value. We call it principal, right? Call it principal. We use P to denote that, or the present sum of money, how much money we have. And then there's the interest rate that, per period, interest rate, say 10% or 5% or 2%, whatever you have. And also the number of periods you need a calculation. For example, all right, I'm saving $1,000 in my bank, right? That's my principal, and the interest rate for that is 2% per year. And if I put in a bank for 2 years, then I want to calculate how much money do I have after 2 years, right? So how much money do I have in 2 years? We use a future value to demonstrate that, to denote the future value of the money. Then the future value of money will be equal to, if we only consider about the simple interest, which is P, which is our present value of the $10,000, plus, right, P, principal, times interest rate, times how many periods, right? Times how many periods. In another way, you can write the equation like this, right? So we can get how much money do I have, right? Well, compared to simple interest, there's also another type of interest which is called compound interest. So compound interest means it's interest on top of interest, right? So interest is calculated based on the principal and the interest owed from prior periods, right? And the calculation can be this equation. So F is future value, and P is the present value, and I is interest rate per period. And N will be the number of periods. So this is the compound interest. Now let's use two examples to demonstrate that. Okay, so for the simple interest rate example, you loan $10,000 to a friend for 5 years at 10% interest. So how much will you get at the end of the 5 years, right? Well, based on the simple interest rate, as long as I know the interest rate, as I know the number of periods, I can simulate and use the principal times the interest rate times the number of years, right, or number of periods. So we can get $5,000. So this is the interest will be earned. And then how much money you can get at the end of 5 years? I'm going to use the present value plus the 5,000. Present value is 10,000, and the 500 will be added on that. It will be $15,000. So this is a calculation based on the simple interest. Now, what about the compound interest? Then what's going to happen? Well, the compound interest, same thing, right? With interest of 10%, for 5 years. And what happens is, when at the beginning of the first year, you have $10,000. Well, at the end of the first year, what happens is you will earn some interest, which is $1,000 because the interest is 10%, right? So at the end of the year one, what happens is you will get $11,000. All right, so no problem, right? It's the same as a simple interest. But on the second year will be a different story because in the second year, the original present value will be $11,000. So it includes, right? It includes the interest you earned from the first year. So that's why it's called interest on top of interest, right? We are using this as the money at the end of the last year to calculate this year's interest, right? So this is then you will get a different value, which is $1,100. And interest rate and total amount of money will be receiving at the end of year 2 is $12,100. Right. Continuing this process, you will find out the actual amount of value. Actually, the friend over you is $16,105.10. You see, it's actually $1,000 more. $1,000 more, right? Okay, so one term we're going to talk about is equivalence. So equivalence means, what is equivalent? What is the current or present value compared to the future value? Right, future value, and we use equivalent to that. So, for example, a loan of $10,000 is actually equivalent to $15,000 after 5 years by 10% in simple interest. And for this case, a loan of $10,000 equivalent to $16,000, $105 after 5 years at 10% compound interest. Right. So you can tell the equivalence is really dependent on the interest rate. Right, depends on the interest rate. If we change the interest rate to 5%, the future value will be a different number. It's very easy to understand because think about, say, 30 years ago, you have $1,000, right? Think about how much you can buy, how many stuff you can buy. But now, 30 years later, you have $1,000. It's a totally different story, right? It's not equivalent. But how much? What is equivalence to the $1,000 30 years ago? Then you have to look at what is the inflation over the years, and then to calculate, what is the equivalent value, right? So this is the equivalence or means. All right, next, when we are doing calculations or when we are doing products evaluations, and we know there are inflows of the income and also the investments. Usually we use cash flow diagrams to help us to understand what are the cash flows over time, right? So the cash flow diagram is simply a graph. It's a graph representing the cash flows, over the years, over the time scale. It can be years, can be days, can be months or weeks or quarters, as long as know the interest rate, right? And so cash flow diagram basically summarizes all costs and benefits over time. And the cash flow diagram is composed of a line and also some segment times and also all the inflows and outflows of the cashes, as well as interest rate, right? two concepts, present value and the future value. We already talked about that, but how do we calculate the future value, present value? So for example, if I have principal or present value, and we want to find out future value, if we are given interest rate, we can use this equation, 1 plus r, the interest rate to the power of how many periods, okay? How many periods. Similarly, if you want to find out P, right, you are given the future value. Now we want to find out what is like this, right? P, you want to find out the future value. Then how do you kind of convert that, right? So basically, you can use this equation and then to find out what is the P. So P equals to I times 1 plus R to the power of negative N. So this is how we calculate the P and F. So for this course, all right, unless it is specified, we just assume everything will be compounded, right? Interest rate. Everything will be compounded interest rate. This is our default case for engineering economics. All right, so we are given this table. So the table shows, at time 0, there's a positive $100. At one time period from today, it's negative 100. 2 times from today, it's positive 100. And then we get all the cash flows. Now we can draw this cash flow diagram. So cash flow diagram really starts from 0. It's not from 1. Keep in mind from 0. Why is 0? Think about this case. Okay, during the year you are depositing a certain amount of money on January the 1st, or January the 1st at 12 a.m. First second, right? Right? So this is time 0. You want to invest in money, and then after 1 year means, okay, now you are withdraw this money exactly 1 year after that. So will be December, or say maybe December 31st, 11:59 second, or the same, right? So this is this during this whole year you gain actually the interest rate, or you gain some of the money. So this is why it's from 0 to 1, from 1 to 2, from 2 to 3, from 2 to 4, 5. So this is how many years. How do you look at this time scale? Okay. All right, now so time 0 now is now. And the first one is positive 100. So in the cash flow diagrams, we gonna put all the positive values or the profits. So profit means the money will get into your pocket, right? So the money will get into your pocket means you get profit. And to be positive and go up, the arrows is going up. See, the arrows going up. And if we are losing our money, so means money is getting out of your pocket, then what happens is we're gonna put those cash flows downward with the arrow. See, the arrow will also reflect the amount of money. So a shorter arrow means the value is smaller amount, while the longer arrow means there's a larger amount of money. Okay. All right, so another thing is you probably want, when you are giving some stories or giving some situations, you want to tell, is that a profit or is a cost, right? Sometimes it can be confusing, sometimes you might make wrong decisions, but you have to be clear out what is profit, what is the cost. For example, if you are investing, right? If you are investing a project, or you are investing some money to something, is it a profit or is it a cost? At time 0, it's actually a cost, because you are putting your money out, right? You are putting your money out. Well, what is profit? The profit will be, after some years, after the project's done, you will get money back, right? Back in the pocket. Then that's the profit. That will be the arrows going up. But your initial investment will be actually the downward, the cost, negative. This is how you draw the cash flow diagrams. Well, another important component of the cash flow diagrams is actually the interest rate. Right? Interest rate is also important because we want to know that what is interest rate during those times. Make sure when you are drawing a cash flow diagram, always have those the time scale, the arrows, cash flows, as well as the interest rate. All right, now let's use one example to show how do you draw cash flow diagrams, how to use cash flow diagrams to help us calculate the amount of money. So this is one example for investment $2,000 now, which is times 0, $2,500 2 years from now, and $3,000 4 years from now, and at an interest rate of 5% compounded annually. Remember? So each year is 5%, and it's compounded annually. What is the total amount you can withdraw 6 years from now? All right, we know the interest rate is 5%, and now let's look at what are the inputs and outputs, or in other words, what are the benefits, what are profits, what are the costs, right? Remember, for investments of $2,000, so investment is actually giving out of money, right? You are putting money money out of your pocket on something else. So that's negative 2,000, at times zero. Okay. So 2 years from now, so 1 year, 2 year. 2 years from now, $3,000. $2,500. Another investment. It's this investment, right? So 4 years from now, 4 years, 1, 2, 3, 4. 4 years from now, we have 3,000 investment, right? And an interest rate of 5% common annually. So what is the total amount you can withdraw 6 years from now? Okay. All right. So we know all these cash flows, 2,000, 2,500, and 3,000. We want to find the future value at the end of the 6 years. So basically, we are looking for the future value, right? Remember from this equation, future value, right, equals to present value times 1 plus the interest rate times to the power of n. All right, for this $2,000, in order for us to move this $2,000 to 6 years, we use this equation. So this is a notation that is really important in engineering economics because in a lot of the calculations in a lot of projects, people prefer to use notation instead of using actual equations. Right? So this notation means, so let's look at it here. This notation means, okay, there are two notations, and I'll start with the first one. So if the P equals to F, parentheses, P, there's a bar, F, comma, interest rate, and N, right? So the A denotes the equation of P equals to F times 1 plus the interest rate to the power of negative N. So it means we know the future value. We want to find the present value, right? We know the future value. We want to find the present value. Right? We want to find the present value. So it reads that find the present value given future value, interest rate, and cash flow periods. Right? Find the future value. Find the present value here, right? Given what? Given future value, interest rate, and number of periods. So this is the notation what I mean. Or on the other hand, if you want to find the future value, right, we just use this notation, means that given present value, we want to find the future value, right? We want to put the future value before the bar. So this is something we want to find. We want to find the future value given the present value, interest rate, and the number of periods. Right? So this is what the notation tells you. And for this finding the future value, the equation will be P times 1 plus interest rate to the power of n. And it reads, find future value given present value, interest rate, accounting for the periods. All right, now after we understand this, now come back to this equation, right? So the first $2,000 converted to the end of 6 years will be $2,000, and we want to find the future value given present value, which is 2,000, given interest rate is 5%, and the number of periods, right? Same with $2,500. But remember, $2,500, we only need to convert 4 periods because this occurs at the end of 2 years, right? We only have 4 years left. So this only convert 4 years. Will be find the future value given the present value $2,500 and add the interest rate of 5%, a period of 4, right? 4 years. Same with $3,000, right? $3,000 given to find the future value, the item 6 years, given the present value of $3,000 at the 5% interest rate and 2 years of periods converting. So this is what the equation shows you and how to write out this equation in order to find the future value. Well, doing this calculation will require you to use those equations, for example, those kind of equations. But also, if you are using Excel, there are an easy way to do that, right? There are very direct equations you can to calculate those equations. For example, enter in Excel the equation that FV. You will see an equation shows up like this. Right, first one is rate, the second one is the NPER, next one is the PMT, and then you have this PV and type. Here, the first one is rate. Rate means the interest rate per period. Right, NPER means the total number of payment periods. So the payment period, number of payment period. And PMT means the payment made each period. It must be entered as a negative number, right? So here, because you have to enter as a negative number. Why is a negative number? Right? Why it's a negative number? Because you are looking for a future value. For example, like this, right? Yeah, originally it's negative during investment. Now you want to know how much you get. So if you only find the absolute number you want to find out, it doesn't really matter that much. But in the equation, if you put the positive number at the PMT, what happens is it will show up a negative number for your future value. So this is why you need to enter a negative number for payment made. There are also two other optional parts you can enter into the Excel. And here are the equations. For example, the present value of the future PV is the present value of the future payments. A amount is assumed to be 0, must be entered as a negative number. It's optional though. Well, time is same thing. It's optional. Usually, what you do is, if you only find the future value, you only enter the first three parts, and then add the parentheses, and then you can get the value. Okay. All right. So this is how to use Excel to do those calculations. All right, so you can actually find the value here as $9,026.45. Another way that you can find out is there are interest rate you can get for for these values from tables, interest tables. There's a compound interest table that is available online or from engineering economics books. And as long as you have this, for example, you have the 5% interest rate, you have how many years, you can check on a table from and find out what is this part of the value. I also attach the link of the table at the end of this lecture. You can use that link to find out the values. Of course, another way is to use Excel, right? All right, next let's look at effective interest rate. So we talk about interest rate, but what is effective interest rate? So first definition of effective interest rate is what would the equivalent interest need to be if we put the same amount of money in the bank as simple interest investment. So do you understand what it means? It's what is the equivalent interest? How much money you will get, right? Equivalent money you of the interest money you will get. If I simply just put the same amount of money, that is what? That is with simple interest rate. It's not compounded. It's a simple interest rate. Now let's use one example to look at this. All right, $1,000 invested at 5% per year, right? 5% of the year, and if it is compounded monthly, what is the effective interest rate? And if it is compounded daily, what is effective interest rate? What does it mean compounded monthly? What does it mean by compounded daily? So compounded monthly means, okay, this month, right? 1, 2, and then 12, right? 1, 2, 12. All right, so compounded monthly means we have interest rate here, and then in the second month, it's interest on top of interest, right? It's on top of interest, and it's on top of interest. There will be 12 periods, 12 times of compound times, right? Well, if it is a daily, what happens is during those there will be 365 days, and it will be compounded how many times? 365 times of those interests, right? So there are more times of interest. And how do we find out what is effective interest rate if we know the nominal interest rate, right? So here when I say the 5%, right, for a year, it's a nominal interest rate, right? It's nominal interest rate, and here this equation, the effective interest rate equals to 1 plus using the nominal interest rate divided by number of compound periods. If it's monthly, then it will be 12. If it's daily, then it will be 335, right? Minus 1, right? We use this equation to calculate what is the effective interest rate. Now let's look at the first one, A. All right, if it is compounded monthly, then the effective interest rate, we use this equation, we can find out that actually it's 0.05116. It will be 5.116% of the effective interest rate. Means what? What does it mean? It means we will need 5.116% in simple interest rate if we want to earn the same amount of money as 5% is compounded monthly. Right? So, for example, if you're going to go to a bank, right? You want to invest $1,000, then maybe the banker will tell you have two different options, right? Two options. One option is it will give you a 5% annual rate that is compounded monthly. Right, 5% compounded monthly. Another option is I'll give you 5% of simple interest rate. Then you want to think about, okay, it looks the same, but 5% compounded monthly will be different with 5% of simple interest rate, right? Because 5% compound interest monthly is only equal to the same amount of money when it is 5.116% of simple interest rate. If you are using 5% simple interest rate, means you are actually getting less interest. You know what I mean? Right? So they're actually getting even less interest. So this is what it means. Well, similarly, now let's calculate B. The effective interest rate for B will be 5.127. So you can see actually the more periods you compound, right, within a certain time actually the higher interest rate actually you effective interest rate, right? All right, now let's so in the second case it means what? It means we will need 5.127% in simple interest rate if we want to earn the same amount of money as 5% is compounded daily. Right? Same as what I described before. You go to the bank, and then the banker will give you two options. Maybe someone is tricking you. That, hey, you have two options. One option is I'll give you 5% of the compounded daily interest rate. Another option is I'll give you 5% of the simple interest rate. Both are annual interest rate, right? Both are annual interest rate, but one is compounded daily, and the other one is compounded. Another one is simple interest rate. But the interest you gain are different, right? Because if you choose 5% of a simple interest rate, actually you earn less money. Why? It's because 5% of compound daily interest rate is only equal to the same amount of the money when you have a 5.127% of simple interest rate. Right? You understand that? So think about what I said. Go back and think about this and see if you can understand why it means it's higher actually simple interest rate. So this is called effective interest rate. All right, next. So this is the one. Another example shows 12 months monthly payments of $100 at an annual interest rate of 18% compounded monthly. It asks us to find the present value, right? Find the present value, the cash flow series, right? All right. So first we know that the 18% of compounded monthly, the 18% of the interest rate is what? It's a nominal interest rate, right? Nominal interest rate. And how many periods we have? Because it is a compounded monthly, right? It's compounded monthly. Month by month, the interest are on top of each other, right? So because it's on top of the monthly, then basically it's the same as 1.5% is each of the months. For this is more the effective interest rate is 1.5 compounded monthly. Well, the effective interest rate, if you want to gain the same as what? If you want to gain the same as simple interest rate, right? We want to find the effective interest rate. So effective interest rate for that will be 1 plus 1.5% to the power of 12 minus 1, right? And minus 1. And equals to what? Equals 0.1956, right? So the effective interest rate we get is actually 19.56% of compounded annually, which means that you go to the bank, and then the banker will tell you that, okay, we have 18% of the interest rate compounded monthly. Well, 18% of course is the annual interest rate, but it didn't tell you that it's the nominal interest rate. And another option is we have 18% of simple interest rate, right? 18% simple interest rate. And it's annual. Well, in this case, we ask you which one to choose. So if you choose 18% simple interest rate, means what? Means actually you are losing profit, right? You are losing money, but you are not gaining as much profit as 18% compounded monthly Because if you're going to gain the same amount of money, you will have to need a simple interest rate of 19.55%, right? 19.55%. So this is the effective interest rate. All right, so just now we're talking about the payment period actually equal to the compounding period, right? For example, monthly payment, and we tell you the interest rate is say 5% or 18% compounded monthly. Then it's the same. But there are some of the times that payment period is not equal to the compounding period. What does it mean? Let's look at the graphs here. All right, so the first one we have what? We have the compounding period is actually this long, but the cash flow payment period is actually this long. Is this long, right? So basically it's 2 times, the compounding period is 2 times the payment period, right? Then in this case, how do you find out if its payment period is actually less than the compounding period? How do I know the interest rate per payment period, right? What is the calculation for that? So because it will be different. Well, it's not 1.5, it's not simply 1.5 divided by 2, but how do we find out this, right? Another thing is, if the payment period is actually longer than the compound period. For example, this, right? Compound period is actually what? Is this long? Is this long? But the payment period is 2 times or more or longer than the compounding period. Well, in this case, what is the interest rate, right? What is the interest rate for the payment periods? So these are the situations we will also see a lot, when we are doing engineering economics calculations. Well, in this case, how do we calculate the new interest? How do we calculate this interest rate? How do we calculate this interest rate? Now we gonna use this equation to calculate that. So the first, the effective interest rate equals to 1 plus r divided by m to the power of m divided by k. What does it mean? It means, all right, so r is what? Nominal annual interest rate, right? And nominal annual interest rate. All right, we talk about what is the nominal annual interest rate. And m is the number of compounded periods per year. It's a number of compounded periods per year. And K means the number of payments per year, and C is number of interest period per payment, right? Per payment. So also, you can just m divided by k. You can use divided by k to be C. All right. Now let's just use one example to demonstrate that. Our example is 12 monthly payment of $100 at annual interest rate of 18% compounded monthly. Find the quarterly interest rate, 7 monthly interest rate. Okay, we know the annual interest rate is compounded monthly. So 18 is what? It's a nominal interest rate, which is R, right? 18 is with the R, right? It's a nominal interest rate. We know it's compounded monthly, right? Compounded monthly. So M will be what? M will be the how many months per year, right? The 12. How many months per year? Because monthly. And now we want to find out, okay, quarterly interest rate. First, quarterly interest rate. How do we find the quarter interest rate? An easy way you can think about it is, a quarter is how many months? A quarter is 3 months, right? So quarter is 3 months. Basically, the quarter or the new period is actually a ratio. So here, see this part, this C or M divided by K is actually the ratio of how many times, right? How many times of what? Of M. of M. If you look at it, is M is what? M is the compounded periods. Compounded periods. So the compounded period is monthly, 12, right? It's 1 month, right? And the quarter is how many months? 3 months. Then to the power of 3. To the power of 3, right? So this is a basic. Here we get a basic period interest, right? Using a nominal divided by how many periods? Compounded periods. And then this is the ratio of how many times of the basic period. It's 3 times the basic period, right? From this, I think it's easier to understand this equation. Now let's look at semi-monthly interest rate. Same thing. Okay, we use 1 plus 18% times divided by 12. We got this kind of basic interest rate, nominal based on the nominal interest, right? Divided by 12. This is the basic period is what? It's monthly, right? It's a month. It's a month. And what is the 7-monthly interest rate? 7 monthly is half, right? So we 1 divided by 2. It's half of this basic period. That's why it's 12 divided by 24, right? 12 divided by 24. If you want to look at the equation this way, I think it's easier to understand how to do this convergence. All right, so now we can find out the actual effective interest rate for the quarterly is 0.0457. It's 4.57%, and 7-monthly interest rate is effective interest rate is actually 0.75 percent. All right, so this is about effective interest rate per payment period. And now let's look at one more example about this. And the example is, what size monthly payment should occur when $10,000 is borrowed at 8% annual interest rate compounded quarterly, and the loan is repaid with 36 equal monthly payment. So we know we want the cash flows are what? The payments are monthly, but our compounded period is quarterly, right? So we know the quarter is what? It's 3 times of months. So the first thing we want to find out is, okay, because the compounded period are different with the payment, then we need to find out what is the monthly interest rate, effective interest rate for the month, right? All right, how do we find it? Then we just use one equation to see I equals to 1 plus R divided by M to the M divided by K minus 1. And look at this. Oh, sorry. So 1 plus nominal interest rate is 8%, 0.08, right? So 0.08. And divided by what? Divided by 4, because how many compounded periods? It's 4 compounded periods during this 8% annual interest rate, right? 4 periods. So 4 periods. The quarter is a basic period. Now let's look at what about the months. What is the monthly payment? Month versus quarter is what? It's a third, right? It's a third. So it will be a 1/3. That's why 4 divided by 12 is 1/3, right? If you want to use that way to to think about this equation. But if you want to use M and K, M will be how many periods of the compounded period divided by how many periods of new payment, or the cash payment, or the payment period will be 12, right? And then minus 1, you can get the effective interest rate for months. All right, so after we calculate this effective interest rate, it's not over yet, because what it's asking here in this question is what size monthly payment should occur. So which means what is the monthly payment amount? Right? What is the monthly payment amount based on this interest rate, or based on this effective interest rate of 0.6%, right? All right, so this is how we converted from quarterly interest rate to to the monthly interest rate. All right, so in order, the second part is to calculate what is the monthly payment. In this case, we first need to look at one equation from present value. How do we calculate? Monthly value or equal payment value. So we use A to denote the equal payment formula, equal payment value, right? Equal payment. So if we look at this equation, we know, okay, these are the A's. These are the A's. This is the A. These are all the A's, right? What is the equal payment of the period? Same. These are the A's, right? Time 0 will be the present value. In the end will be the future value. And these are A's. All right. So if we know the present value, the interest rate, and the number of periods, how do we want to find out? How do we find out A, the equal payment, right? How do we find out the equal payment, right? So we use the equation of this equation, use this equation to find out the equal payment. So that will be what? That will be, we have the cash flow here, and we have a present value, or suppose you have a loan. Let me get rid of this part. We have a loan, all right? You got a loan here, which is P, and you want to pay it back, right? With equal period, and A. They are all, suppose they are all the same. They are all the A's, right? So now, if we know the P, how do we want to find the A? So basically, this is what it shows with this equation, right? And A equals to P times I, the interest rate, times 1 plus I, the interest rate to the power of n, divided by the lower part. So this is how we calculate that. Well, if you're going to try it in Excel, this is the equation in Excel. Right, so use PMT, so payment, basically the payments, right, monthly payment, and rate is interest rate, NPR is the number of payment for the loan, number of payment for the loan, and the PV will be present value, and the other two optional items. And all right, so we know this is equation. Next, I want to do is when I use this equation, because we already know the interest rate, right? The effective interest rate will be 0.66%, right? Basically, we just replace I with 0.66, right? So the parentheses part will be 1.0066, right? All right, and 36 will be how many periods of the payment. So it'll be 36 periods, right? 36 periods. You want to find, and then eventually you can find the A value is $313, which means if you want to pay that back with that interest monthly interest effective interest rate, then the monthly payment will have to be 313. So because there are a lot of calculations, for some very basic calculations that won't be described in too much details. For example, how to do the calculation here, I think you all know, and it's very basic calculation skills. I just skipped here, but doing those kind of calculations actually takes a little bit of time. If you want to do it, manually. Another way is use Excel. If you use Excel, it probably be a little bit quicker. But if you use Excel, you need to know this notation, right? How to use this notation to help you understand or write down what are the calculations instead of writing the full equation there. All right, so this is effective interest rate per payment period. Now next, let's look at MARR. So MARR means it's a minimum attractive rate of return, or minimum acceptable rate of return. So basically, that is a standard, right? That's a standard or something you want to compare with, right? It's not something that actually happened, but it's a standard that you for your decision making, and also it is the interest rate to evaluate projects, right? So usually it's not something that's determined by the bank. It's more of a return from how much you invest to how much you gain, right? So this is the MARR. All right, so for the decision-making criteria in order to evaluate projects, there are multiple ways. For example, the first is the net present worth, net future worth, capitalized worth, annual equivalent worth, payback period, discounted payback period, rate of return, benefit cost analysis ratio. These are all different decision criteria. In the next few slides, I'm gonna talk about each of the decision criteria, and I'll give you an example of how do you calculate based on each of, how do you solve problem based on each of the decision criteria. All right, first, net present worth or the net future worth, basically they are very, very, very similar. The way is you just need to convert everything into net present worth. Means you are converting everything to time zero, right? Converting everything to time zero. And for example, this it shows that given the MAR is 10%, perform a present worth analysis of the two machines with the following costs. Okay. All right, we know the MAR in this case, which is the interest rate, right? And also know that for machine A, the first cost or the present value is present investment is $2,500, and the annual operation and maintenance O&M cost is $900, and the salvage value is $200, and the lifespan will be the 5 years. While compared to B, the first cost will be $3,500, and annual O&M is $700, and salvage value is $350, and same, the lifespan is 5 years. Well, you can see from the causal loop diagram that where are these cash flows, right? The 2,500, 3,500, all these annual costs. All right, so next what we're going to do is, if you want to use net present worth as a decision criteria to compare the two machines, then we're going to convert everything to the time zero, which is the present worth, right? So the $2,500 converted to time zero, because it's already time zero, so we just put it here, right? It's a negative $2,500. Well, next part will be what? It will be the $900. Because the $900 occurs at each year, 1, 2, 3, 4, 5, each year, then how do you want to convert these $900 back to time zero, right? Remember, we have the equation, right? We have the equation. What equation? Equation of converting P and A. So P equals to what? A times what? 1 plus I to the power of n minus 1 divided by what? Divided I times 1 plus what? I to the power of n. So this is the equation. Or in other words, in the notation, in engineering economics in notation, you can see find P given what? Given A, right? Given what is the equal payment amount at the interest rate of 10%, or the MAR is 10%, and number of periods. How many number of periods? 5 periods of equal payments, right? And what is A? A is $900, right? So use this notation to show that we are converting all the $900 during the five periods at 10% interest rate back to time zero to find this P, time zero. Same thing here. Now it means if we know the what? If we know the future value, which is $200 at the interest rate of 10%, and how many periods you are converting back? 5 periods, because $200 is a salvage value. It occurs at the end of 5 years, right? And to the future value already given is $200. Now we're converting back to P, right? Present value. In this case, you can either use Excel or use the equations to calculate eventually the value we'll get is negative 5,788, right? And now we calculate machine A. Same. You can use the same way to calculate machine B, and the value is actually negative 5,936. Now you can compare the two, right? So comparing two, you can tell that the present value or present worth analysis actually machine A is actually smaller than machine B, which means that what? Which means overall, over this long project, 5 years project, actually machine A's investment is actually costs less money, right? Machine A's investment costs less money. So this is how you use net present worth to calculate this to make decisions based on comparing of the two projects. All right, next, look at this. Before we get into the next slide, let's look at this first. The lifespan of the two projects are actually the same. It's 5 years. Both are the same year. So what happens if the lifespan are different, right? So machine A is probably can last longer, while machine B probably lasts shorter. In this case, what's going to happen? Or when the two projects or two comparing of the alternatives lifetime are different, how do we make comparisons, right? So here you always need to remember that comparing alternative over a common period of time. You cannot directly compare two or more alternatives based on different period of times. You have to make them as a common period of time, right? Simply, for example, in this case, simply compare machine A and machine B at 6 years and 9 years, converting everything, over 6 years back to zero, converting everything over 9 years back to zero. It does not make comparison because it's not fair comparison, right? It's not a fair comparison. So in this case, what we do is we want to make all of them actually have the same common period. So the common number of life of 6 and 9 is actually 18 common period, right? It will be 18 years or 18. Well, in this case, 18 for the first project of machine A, how many periods do we need? How many, this whole period we need? It's actually 3, right? 1, 2, 3. 3 times 6 equals to 18, and 2 times 9 equals to what? Equals to 18. All right, now we can see they are on the same beginning and end. In this case, we can make the comparison, right? All right, if you want to make the comparison, we need to do a lot of calculations to make sure that we convert it back to zero. Well, how do we do these calculations? Somebody may think, okay, now let's just do this one calculation that negative $11,000. This is the investment, and this is how to use the equal payment to find the present value, and that's 6 years. And we know the future value to find the present value in the 6 years at the rate of 15%. Well, this calculates one period of the present value, right? And if you use 3 times this, does it work? Absolutely not, right? Because remember, if you are looking at the 18 years, right, multiple time scales, we are counting the interest rate and compounding the interest rate in there. And this 11,000 definitely is not equal to this 11,000. So that's why you never do this simple multiply. It's not right. So what should we do? We should calculate all those cash flows back to time zero. All these cash flows, convert all these cash flows back to time zero. So these are 11. This is the first 11,000, right? This is the second 11,000. This is the third 11,000. Given the future value times the find the present value. And then the first 35,000. The 35,000 will be the same, right? 35,000 will go through all the 18 periods. That's why it's using 18 period of time. Then this first $1,000, second $1,000, and third $1,000, you can be converted, at different time periods. Then we get the present value to be 38,559. So this is the right calculation. The way of calculation. Okay. All right. Then for machine B, same. We cannot just simply times 2, right? We have to convert everything back to 0, and after the calculation, we found out that the present worth is 41,383, and you can see. Compare the value here. This one is 38. The next one is 41. So that's why the present worth A for machine A is actually smaller than or less than present worth of machine B. So in this case, machine A should be selected. So this is how we achieve the comparison if they have unequal lives. All right, next, let's look at another decision-making criteria, which is capitalized equivalent. So capitalized equivalent means when we are comparing the projects that they have a very long time and is or perpetual or have the infinite time period. Right, a lot of those projects are actually going to last really long. For example, government projects, bridges, roads, or long buildings, or some funds, investment, and it usually is called the money need upfront, such the interest earned will cover the cash flows requirement forever, right? So this is a kind of perpetual project calculation with capitalized equivalent. And how do we do that? And how do we find out the present value? Basically, we know the A, we want to find out the present value, right? So remember, if we know the equal payment, right? If we know the equal payment and want to find the present value, we use this equation, right? The P equals to A times this equation. Well, the difference is that the time horizon is really long or it's infinite, which means n is going to infinite, right? N is going to infinite. Now, if you look at this equation equals to what? Equals to an A times what? Times 1 over I minus A divided by I1 plus I to the power of n. So if what? If I is going to infinite, it means this part will be 0, right? This part will be 0. This part will be 0. Okay? So which means this part will be 0. Well, in this case, we only have this part left, A over I, right? A over I. So this is a equation we left that we can calculate that. All right, let's use one example to look at this. So, for example, this example shows that to sustain an endowment that it will produce $12,500 per year at 4.5% interest, the initial sum will have to be 2,077 this number of dollars. But why is that? Why is that? We use this equation, right? So the equal payment or the equal cash flow is $12,500 per year, right? $12,500 per year, and the interest rate is 4.5, so 0.045. Then we can calculate what is the present, right? We know this and calculate what is the present value for that, which is $77,778. And so which means that to sustain that endowment that it will produce $12,500 per year at 4.5 interest rate, then the initial sum, the money you need to make is actually have to be this amount of money. So this is a perpetual project. Remember to use this equation to calculate. All right, the next decision criteria is annual equivalent worth analysis. Actually, this is it's very simple to understand because for the present worth analysis, what we did was we convert all the cash flows to times 0. Well, the annual equivalent worth analysis means we convert all the cash flows to the equal payment, to the A, right? Convert every future value to A, present value to A, right? Convert everything to A. All right. So now let's look at some decision criteria here. Is okay if the A or the annual equivalence is bigger than 0, it means what? It means we're actually generating more money, right? It's positive cash flows, right? It's positive cash flows. And if it is less than 0, means it's negative cash flows. If it is equal to 0, means it's indifferent. It's it's break even. It's break even. So this is the decision rules how you do that. Now let's look at one example for this. All right, so a 500,000 investment in a machine is being considered. Okay, 500,000 investment in the machine is considered over a 10-year planning horizon. It is estimated that the machine will produce net annual savings of $92,500. While at the end of the 10 years, it is estimated that the machine will have $50,000 of salvage value. So based on a 10% MARR and an annual equivalent worth analysis, okay, should the investment be made? Okay, we have 10% of the MARRs to compare with. Should this be made? Sorry, it's 10% of MAR as the interest rate. So in this case, should the investment be made? All right, now because a lot of those the cash flows are already in the equal payment, right, or in the annual payment. All right, and only 2 cash flows are actually not annual payment. Then we probably want to convert those into annual payment, right? Convert 500,000 and convert 50,000 into annual payment. Now we just simply use the equation to calculate that. All right, so the first $500,000, because it is a present value, you want to convert it to annual value. Then we want to use the equation that given the present value, 10% interest rate and 10 periods, and the present value is this. We can use this to find out what are the equal payment during those periods, right? And of course, 92.5, because it's already the equal payments, we do not need to convert. We put 92.5 here, and another one is a 50,000 salvage value, or the eventually salvage value. They want to convert this value to what? To the annual equivalent, right? To the equivalent payment. Then we use future value is this, and interest rate is 10, and 10% of on a 10 periods. So we can find the annual interest rate. So from this, we can do the calculation and find out that the annual was is actually $14,264.57. Well, in this case, because it is bigger than zero, right? It's bigger than zero means we have positive annual cash flows, right? We can have positive annual cash flows. In this case, we can accept the project, okay? Remember the rules here. These are the rules. Because we have positive, so we can accept the project. All right. So next decision criteria is the rate of return. So the rate of return means is the interest rate earned on the unpaid balance of a loan, right? And it's also the break-even interest rate that equates the present worth of the project's cash flows to the present worth of its cash flow inflows. It's outflows and inflows. If it is equal to each other, we want to find out what is that interest rate. So that rate is the rate of return. All right. So how do we calculate the rate of return? And we can use a equation setup that like this: the present worth value, right? So we convert all the inflows to the present worth, convert all the cash flows of all cash flows to that present value, and let it equal to 0. Let it equal to 0, right? Let it equal to 0. So if it is equal to 0, then the interest rate we get is what? Is the rate of return, right? Rate of return. And how do we make decisions based on rate of return? We want to use this ROR, the rate of return, to compare with MAR. Remember, MAR is the standard we want to compare with, right? It's acceptable or not, right? So if the rate of return is bigger than MAR, means you got a higher return than the standard, right? Than the comparison. So if it is equal to, it is indifferent. If it is smaller than MAR, means we got less returns than the standard. So that's why this is how we calculate it, how we make decisions. Well, our R can also be solved using other ways. Basically, all you need to do is to find out it has to be 0, right? The inflows have to be equal to the cash flows in order to find the interest rate of return, right? You can also convert everything to present worth. You can also convert it to everything to future worth, or you can also convert everything to annual worth, right? But they all have to be 0. Just remember, we cannot rank projects by rate of return. So why? Because rate of return is a ratio, or it's a rate, right? It's a rate. We cannot compare projects based on the rate. Why? It's because rate does not describe the absolute values. Think, okay, if you increase from 0 to 1, it's what? It's really big amount of increase, right? Increase rate. But if you want to increase from 99 to 100, what is the rate? What is this rate of increase? It's very small, but it's the same, right? But it's the same. So that's why we cannot use ratios or rate of return rate to compare projects, because it does not describe any of the absolute value of the projects. Okay. All right. Now let's use one example to demonstrate how to use rate of return for this calculation. Same example as before. We already know the setup. Now, the thing is, we do not know what is the rate of return here, right? We do not know what is return here. So it only says, okay, we have the 500,000 investment in the machine. It's a 10 years planning horizon. As estimated, the machine will produce a net annual savings of $92,500,000. At the end of 10 years, the salvage value will be $50,000. And what is the rate of return of this investment? Okay, so all right, in order to calculate the rate of return, then we'll have to do what? To let it inflows and outflows equal to 0. Okay, let inflows equal to the outflows, or inflows minus outflows equal to 0, right? So now let's convert everything back to present worth. So converting back to our present worth, $500,000 the same. Then we convert everything to present value from the A. We already know the A, no interest rate, we have the interest rate, we have a 10, and 50K is also converted back to a present value given the future value, rate, and the 10. All right, now we have all the numbers except what? Except this interest rate, because we do not know the rate of return yet. This is what we want to find out. But how do we want to find out this value? Right? How do you want to find out this value? Well, because the calculation will be a little bit complicated, of course you can use MATLAB or use some other computer tools to look at. But one way to give a rough estimation will be what? You can try different interest rate and just get a close enough number for this for this rate of return investment. And unless you are doing really accurate calculations, but a lot of times, if you are having exams, or if you are doing, for example, the black belt or the green belt or the yellow belt of the Six Sigma examination, or the professional engineering exams, usually they will not ask you to calculate the complicated interest rates without computer or setup. So in this case, what you're going to do is you can try. If you do not have computers, then in this case you can try the sum of the interest rate and see what are the values, because what we need to find out is that the PW equals to 0. This is what we want to find out, right? So we can try different rates. If we see one is positive and one is negative, right? If we know that one positive and one negative, then we can do what? We can use interpolation to find out maybe what is the name, what is the middle that in it, right? So for example, I tried 10% here. Someone may ask, why do you try 10%? Why do you don't try 1% or 99%? Well, the reason I try 10% is because probably I already tried something else, right? Probably already tried 5%, and it's a really large number. Or maybe I'll also try 8%, right? Large number. Then want to try the next one will be the 10%, right? And then maybe I tried is 50%. Then found out it's a really large negative number. Then probably going to reduce that number and try maybe 20% or 15%. Then want to narrow it down to maybe 10% and 15%. And then what we'll do is we use this interpolation. See, we assume that it's x. The rate of return is actually lies in somewhere in the middle between 10% and 15%. Okay. Same, the 0 is somewhere between 87,000 and 23,000. How do we do interpolation? We use 10% minus this value. Okay, 10% minus this value divided by 0.1, 10% minus this value, right? 15%, and equals to what? Equals the same setup, but its absolute values will be this value present worth minus 0, and this value minus this. Then we use this setup interpolation to solve for x, which is the rate, right? We got 13.95%. Is it accurate? Not exactly. But it is close enough to the number if you calculate it by the computers, right? Because if we are using this linear interpolation setup, means we assume the relation of I with this PW is actually linear, but in fact it's not linear. right? So in fact, it's that's why this is not a absolute accurate number, but it's a close enough number that we can solve problems without the computerized tools. All right, now if next we'll assume that if the MARR, so the standard is 10%, right? Should we consider this project or should we accept this project, right? Remember, MARR is a standard to compare with, right? Because the rate of return here we calculated 13.95 is bigger than the MARR 10%. Therefore, we have better return than 10%. So which means we can accept this project. So this is how we use rate of return to make decisions based on the project's comparisons. All right, so the last but not least is benefit cost analysis. Okay. Oh, sorry. I think this is the second last decision criteria. The benefit cost analysis. It is a very common tool or method to compare projects, and it's widely used in numerous not only just government but also industrial projects as well, right? So basically, the concept is very simple. Means you have to calculate the benefit, you have to calculate the cost, right? So you and there are two different ways to make the comparisons. One is using the ratio, and one is using the absolute values. So ratio will be use benefit divided by cost, and the absolute value will be benefits minus the cost. Well, sometimes the benefit cost analysis is also called cost benefit analysis. It just same concept. Well, the comparison will be the cost divided by benefit, right? And then cost minus benefit. Either way, but this is a way that how to use benefit and cost to make decisions. All right. Now let's look at how do we make decisions based on the benefit cost analysis. So this is the calculation for converting all the cash flows to the present worth of the benefit, and this is converting all the cash flows to the time zero of the cost. Then we use the ratio of benefit divided by cost to find if it is bigger than 1, means benefit is more than cost, right? We accept the project. If it is smaller than 1, means its benefit is less than the cost, reject. Similarly, if benefit minus cost bigger than 0, we accept the project because it's bigger. If it is a benefit minus C, the cost is smaller than 0, means we reject because the benefit is less than the cost. All right, now let's use one example to look at how can we make those comparisons. So alternative routes are being considered by the State Highway Department for location of a new highway. Okay, Route A, costing $4 million to build, will provide annual benefits of $125,000 to local businesses. And Route B will cost $6 million and will provide $100,000 in benefits. Okay, the annual cost of maintenance is $200,000 for A and $120,000 for B, respectively. If the life of each road is 20 years and an interest rate of 8% per year is used, which alternative should be selected on the basis of a benefit cost analysis? Well, so this part A shows all the conditions. So means what? We have 20 years of the lifespan, right? 20 years comparison period. And the interest rate is 8%. Well, Route A, the cost, we have the cost. The cost is $4 million for the initial investment. Okay, $200,000 is annual operation and maintenance, 1M. And that's the cost for A. And the cost for B is, and the benefit for A is $125,000 per year. Similarly, we can find the cost for B and cost and the benefit for B. What is that? All right. Now, if we want to do the comparisons, because of what? Because most of the cash flows are during the 20 years are actually for the annual cost, right? So in this case, we can actually convert all the present value and all the initial costs and to what, to the annual cost, right? So this is how we do the comparisons, and then calculate the annual cost will be for A will be $4 million. We know the present worth. To find out the annual cost given the interest rate and 20 periods, we can find what is the annual worth is this amount, $407,408. All right, and also we have another cost which is $200,000 annual operation and maintenance, right? And the benefit is $125,000 per year. Now we know the cost will be. We know the benefit. Benefit is $125,000. The cost will be the two parts. First part is the initial cost, right, converted to the annual equivalence, and another one is annual operation and maintenance. Then we use B divided by C equals to 0.2058. Remember, if it is bigger than 1, means what? Means benefit is over. It's a cost, right? It's bigger than cost. But in this case, because it's less than 1, means benefit is less than the cost. So we reject route A. All right, now let's look at route B. What's going to happen? Same, we convert everything into annual worth, and $6 million given the present worth of $6 million. Find A with interest of 8% and 20 periods of time. We got this annual worth or annual equivalent money, right, of the cost. Another annual cost is $120,000 operation and maintenance, and this is the benefit, $100,000 per year. And we use this, and also we get the value of this less than 1. So which means what? Which means the benefit is also less than the cost. So also in this case, we reject part of B, right? Well, if you really want to make a comparison, I'll have to choose one. Well, in this case, maybe route A is relatively better than route B. But if you're not generating any profit from this, actually, both projects are losing money, or should be rejected. All right, so this is how to use benefit cost analysis to make comparisons. But remember, in that case, what happens is that we cannot use ratios, right? We cannot use ratio to rank projects, right? To compare projects. We cannot compare ratios. But how can we compare those kind of ratios? Well, how can we compare projects, with more than 2 or 3? Right? How do we do that? Well, in this case, we use incremental benefit cost analysis, right? So incremental benefit cost analysis means we compare 2 by 2, right? And also we have different setups to use use absolute values minus another one. So how it works? Now let's use this example. So consider 3 alternatives provided in the table. So this is the table. And all of the alternatives have no salvage value, okay? No salvage value. If the interest rate is 12%, which alternative should be selected, okay? Step 1, first what we want to do is, okay, we have these 3 alternatives, okay? First thing we want to do is, we want to rank them, or we want to put in a sequence, right? Sequence will be, okay, we put this setup, first cost, uniform annual benefit, useful life in years, and A, because A, the first cost is 50, B is 150, and C is 110, we're going to put in a sequence based on those costs, right? C will be in the middle. So we put C in the middle, and then next we want to do is, we're going to first compare 2 of them, right? Use the middle one minus smaller one, right? Use C minus A, and we are doing this minus was actually is the absolute value of the cash flows. It's absolute value of the cash flows of each year. So it's year 0, 1, 2, 3, 4. right? In year 0, what is the difference? The difference will be minus 60. Then year 2, in year 1, what is cash flow? And after we get all these cash flows, and then what we do is we can calculate, right? We can calculate this cost-benefit analysis, right? We can calculate this cost and benefit, right? We know the cost and also we know the benefit. Now we calculate that and we find out that this value is actually less than 1. Means what? Means what? Means C in this case actually should be eliminated because this is a difference of C minus A, and C minus A doesn't work, right? Means A is actually generating more value here. So A is actually preferred compared to C. Well, if it is bigger than 1, what's going to happen? Means C is preferred than A, right? Okay, because it's smaller than 1, so which means that A is preferred compared to C. Now the next I want to do is, of course, we compare B and A, right? Similarly, we do all these cash flow differences. We find out, okay, these cash flows of B minus A, and then similarly we calculate the cost-benefit analysis or benefit-cost analysis. We find out this value is bigger than 1, which means because we use B minus A, so means B is preferred than A, right? B is preferred than A. So this is called incremental benefit cost analysis, right? So first we put it in sequence and then compare 2 by 2, right? Eliminate 1 and compare 2 by 2. So this is incremental benefit cost analysis. All right, now next, I think also the last one is the payback period. So payback period, the decision criteria means it's a time required to recover initial investment. We have two concepts here. One is payback period, simple payback period. Another one is discounted payback period. The only difference between the two is the simple payback period does not count the time value of the money, but the discounted payback period will count time value of the money, right? And take consideration of time value of the money. All right, now let's first look at this simple payback period, and how do we calculate what is payback period? So basically, if we know the initial cost, we just need to need to find out what is a uniform annual benefit, right? So use that divided by this to get how many years, what is periods to recover all the costs, right? So example here, so a $500,000 investment in the surface amount placement machine is being considered over a 10-year planning horizon. Okay, 10-year planning horizon. It is estimated that machine will produce net annual saving of $92,500. What is the payback period for this investment? Right? We know this $92,500 is annual savings, right? Annual savings. So this is something that is coming into our pocket, right? The positive cash flows, annual savings. All right, and the $500,000 is actually investment giving out of their pocket, and they want to recover that back without considering time value of the money. We simply use the investment divided by 500, so we get 5.4 years. So which means that 5.4 years we can get our payback period. Okay. All right, so next, let's look at the discounted payback period. How do we calculate that? For discounted payback period, because we need to take care of the time value of the money, then basically we have to convert everything into what? Convert everything into the present worth, right? Present worth. Okay, now it's same, and the only difference is that given the interest rate is 10%, and it's asking what is the payback period for this investment. If you want to find out payback period, means the investment equals to the gains, right? Investment equals to the gains. Now the investment we know is $500,000. Well, now we need to find the gains, right? If you want to equal to each other, then all we need to do what? We use the annual worth, which is $92,000. We know the interest rate, which MAR is 10%, but we do know now know the N, and we know the annual worth value, right? So from this setup, and let it equals to 0, we can find, because N is only variable in this equation we do not know, right? All right. So there are two different ways to do this calculation. How to find out the N. So one is, of course, you can use some MATLAB setups to find out this equation, to solve this equation and get the N value. Well, another way is because we do this calculation, we find out that this setup equals to 5.40, right? 543. But one way is we can look up some interest tables. So from this, you can open up this link and find out what the interest table. So interest table means it will give based on the year, based on the interest rate, it will give you this setup's values, right? For example, 1%. 1 year, 2% 1 year, 3% 1 year, 4% 1 year. If you want to find out, P, if you have A, I want to find P, right? Of course, you can change the year. Okay, 1% 2 years, 1% 3 years, and you can find this value from the table. All right. So from this table, actually, you can find out that with this setup, the table's value is actually 5.3349, and if it is 9 years, what's going to happen is 5.7590, right? All right. So in order for us to make sure that it is 0, what we're going to do is we're going to do interpolation, right? Interpolations. Remember, before we were doing a rate of return, we did that, and we found that the interpolation is 8. N should be equal to 8.1663, right? Because the first one is 5.3349, is less than 5.4, and the next one, the 9 years, is actually 5.759. It's bigger than 5.4. We know that this N should be between 8 years and 9 years, right? Should be between 8 years and 9 years. That's why we use interpolation to find this. And now we find 8 years. We can summarize that actually the payback period for this investment is 8.17 years. So this is how we use payback period to make decisions or to compare projects or to calculate the payback period based on the project. All right, so basically this is everything for this lecture. We talk about capacity planning, and also we talk about engineering economics. So engineering economics is very, very important part of this course. And there are going to be a lot of calculations, and this is probably the most calculations we have in this whole course. But it's very important in the future if you are doing the management work, or if you are doing operations related, doing some comparing projects. This is a very basic skill you have to have in management. So do more practices. Especially in this class, I won't be able to do very detailed calculations with you, but I have explained all the principles